So in 1987, I was walking through a career fair at the Wilson Commons here at the University of Rochester. And there was a company there that had this big picture of the primary mirror of the Hubble Space Telescope. And I didn't know much about Hubble, but I talked with the folks from the company, and I was really amazed at how powerful this telescope could be. A few years later, in 1990, NASA launched the Hubble Space Telescope. And it was brought up into low Earth orbit by the space shuttle, and it was deployed, and the first images were sent down to the ground. But there was a really big problem. There was trouble with Hubble. The primary mirror of Hubble was actually ground to the wrong prescription, and all of the images coming from Hubble were blurry. So this was a real crisis for NASA. It was only a few years after the Space Shuttle Challenger had blown up, and so NASA put together a team and decided it was going to fix Hubble. It was already planning on upgrading Hubble, but it had to come up with a way to fix this optical problem. And in about 3.5 years, 2 instruments were built that fixed Hubble. One of the instruments was an instrument called CoStar, which had little arms that deployed with little mirrors that kind of acted like contact lenses to fix 3 of the instruments that were already in there. The second instrument was called the Wide Field Planetary Camera 2, and it was 2 because their Wide Field Planetary Camera 1 was already in Hubble, and the second one had little corrective optics inside of it that took this amazing image of the spiral galaxy that you can see, which demonstrated that Hubble was repaired. There were astronauts who actually did spacewalks to put these instruments in Hubble, but once it was repaired, it was fully operational, and it was able to do the science that it was intended to do. About 2 years later, one of the things it did was take an image of a real dark patch of the sky. This patch of the sky we call the Hubble Deep Field. Basically, Hubble stared at the same dark patch of the sky for 10 days, which was a really long period of time for Hubble. This was about as long as it stared at any one region of the sky. It took over 340 exposures with different filters, and all of this was put together into what we call the Hubble Deep Field. Now, some people, especially astronomers who look at the Hubble Deep Field, have what Einstein called a cosmic religious experience. Because in looking at it, you're actually seeing the evolution of the universe from when the universe was about 1 billion years old to it is today. Now, the Hubble Deep Field is an amazing image of the universe, but it doesn't go all the way back to the very beginning of the universe. And in fact, the astronomers looking at the data from Hubble decided that we needed to build yet another telescope that could fill in the void. The void I'm talking about is really a void in our understanding of the cosmic history of our universe. It turns out that some of the very first light that was generated in the universe came as remnants from the Big Bang. There was this huge explosion and inflation, and there was a slight thermal emission in the form of microwave light that was generated. And actually, 2 satellites that were developed at the institution I work at the Goddard Space Flight Center, have mapped that microwave background. One of them called COBE, the Cosmic Background Explorer, won Dr. John Mather a Nobel Prize. Dr. John Mather is now the project scientist for the Webb telescope. So that was the first very remnants of light that we've seen with satellites. But then there was this sort of dark period where the universe became opaque, because what happened was protons, neutrons, and electrons kind of got together. They formed atoms, and the atoms tended to prevent light from getting through. But at some point, the atoms started to clump. There was little gravity wells. The gravity makes stars. The stars eventually explode into supernova. And those supernova create ultraviolet light that ionize the atoms, and that create light that we can see. And so we start getting stars, we start getting supernova. We start getting to a period we call reionization, somewhere between a few 100 million years after the Big Bang and 1 billion years, which Hubble can see. That reionization period is actually the period when the first chemical elements were formed. Some of you may know that supernova generate chemical elements. Because of the amount of energy you have, what was just hydrogen and helium can now become things like carbon, nitrogen, and oxygen. So if we can see into that epoch of time, we can actually see the formation of the chemical history of the universe. But Hubble can't do this. And the reason is kind of complicated, so bear with me. It turns out that the light from the very early universe has been coming to us over a very long period of time. And that light, the universe itself, while the light has been coming to us, has been expanding. There was the initial inflation, but the universe has continued to expand and even accelerate. And because of that, we call it the mesh of space-time. The mesh itself is expanding. So the light coming to us, which starts as visible light and ultraviolet light, is being redshifted, is being stretched because of the expansion of this mesh into the infrared. And that infrared light is what we need to look at in order to see this early epoch of time. Hubble was not designed to see that light. And in fact, Hubble has a major challenge in being able to do that, which is Hubble's primary mirror, that mirror that I saw at that career fair, is actually operated at room temperature, which is roughly 7 degrees Fahrenheit or 293 degrees Kelvin. And at that temperature, because of something called black body emission, every body produces infrared light, but at room temperature, you produce a lot of infrared light that would contaminate the image that you're trying to see. The mirror itself would generate so much infrared light that you would not be able to see these very dim infrared objects. So if you want to see these objects, you actually need a telescope that's about 50 degrees above absolute zero, about minus 400 degrees Fahrenheit. And by the way, it needs to be bigger than Hubble. Hubble's a 2.4 meter primary mirror. We need a mirror that's about 6.5 to 7 meters in size just to collect enough photons because these objects are so dim. So we need a humongous telescope that's really cold. And that's really the key driver that led to the development of the design of the James Webb Space Telescope. The mirror is so big, it's actually bigger not only than the Hubble mirror, but even the Herschel mirror, which worked at very long wavelengths. And it's so big it will not even fit in a rocket without being folded up. So to fold it up, we literally have to segment the mirror. We actually have 18 individual primary mirror segments. Each one of them has 7 actuators. These actuators move in fractions of a wavelength of light, 1/20,000th the diameter of a human hair, at the temperature of minus 400 degrees Fahrenheit, to align the 18 segments as though it's one monolithic mirror. It'll do that in space. There are wings that have to unfold. The secondary mirror has to unfold. And then to cool it, which was one of the biggest challenges, we're talking about cooling thousands of kilograms of mass to this incredibly cold temperature. We actually do it passively, and we do it by deploying a very large sun shield that's about the size of a tennis court, and that's literally 5 layers. And we do this at a very unique orbit. Unlike most observatories, which are in low Earth orbit, really close to the Earth, where they're constantly seeing the sun and then not seeing the sun, which is the way Hubble works, by the way, Webb is actually going to go really far from the Earth, 1.5 million kilometers, too far to be serviced the way Hubble was. The reason we go that far is there's this unique point there called the Lagrange point. There's actually 5 of these Lagrange points, but the L2 Lagrange point, which is at a point 1.5 million kilometers from us here on Earth, at that point we can actually keep the sun, the Earth, and the moon on one side, put up this large sun shield, and basically block anything that's warm, and let the telescope cool and the instruments. And the only thing the telescope is seeing is the inner layer of that sun shield, which is cold, and deep space, which is even colder. And over many weeks in space, the telescope will cool down, we'll align it, and then it becomes the observatory that's the James Webb Space Telescope. In addition to just a telescope, we also need instruments. And so Webb has 4 scientific instruments, and Webb can do a lot of different science, not just study the early universe. But 3 of the instruments were specially designed to really focus on this early universe science. And they do it in a very complementary way, which is going to make it even more powerful. One of the instruments is a near-infrared camera that kind of picks up where that Hubble wide-field planetary camera leaves off and goes all the way up to a wavelength of 5 microns. It's a near-infrared camera with lots of filters that can take basically the equivalent of the Hubble Deep Field, but in the near-infrared. A second instrument also operates at the same wavelengths, but it's actually what's called a multi-object spectrometer, which is a very unique thing. We didn't have one of these on Hubble. On Hubble, we actually have a spectrometer that just can look at one individual object at a time. What this instrument will do, is it actually has a special technological device that was developed actually by folks at the Goddard Space Flight Center. It's a little MEMS device. MEMS stands for Microelectromechanical Systems. It's a series of little tiny shutters that are each about the diameter of a human hair. And you can program them so that you only open shutters which have, say, a galaxy on them, so that the only thing getting through your instrument are the things that you want to look at, the galaxies, and nothing else. And on each of those galaxies, you can take a spectra. You can spread the light out with, say, a grating or a prism, and actually see the wavelength composition of each individual galaxy. And from that, you can determine the age of each galaxy. You can determine some of the chemical contents of those galaxies. And we can do that and look back during this first epoch of time and see how things evolved in a sort of scientific manner. The third and final instrument actually works at even longer wavelengths than the first two. It's a mid-infrared imager, which picks up where the other two leave off at 5 microns and goes all the way up to the longest wavelengths that Webb can do, which is 28 microns. And that really fills in the extra parts of the spectrum which you would want to look at to understand the really, really early universe. And that particular instrument is very challenging because it has a detector that operates below 10 degrees above absolute zero. So we are very far along in developing this observatory. I've personally been working on it for 16 years since I worked on the Hubble. This past summer, we actually had the telescope and the instruments together. We brought them to the Johnson Space Center in Houston. It turns out that they have one of the largest vacuum chambers on the planet, which is why we went there. We actually had to build a whole clean room to get the telescope into it. We built a helium shroud that allowed us to cool the telescope. We had special optical equipment that works at cryogenic temperatures. We put it in the chamber in July and started our test. And lo and behold, about the 3rd to 4th week of August of this past year, we got the telescope cold enough to start taking the optical data to do the end-to-end tests that weren't done on Hubble. And some of you may recall what happened during that period of time. Hurricane Harvey hit just as we had hit operating temperature. And so 120 people down in Houston made it through Hurricane Harvey. We made it through all of our tests. The telescope looks incredible. I think it was sort of a message from nature reminding us how difficult it is to see the early universe. So now the telescope is actually sent to Northrop Grumman in Redondo Beach, California. And just this week, the spacecraft and sunshield, which the sunshield is now folded up and it sits on top of the spacecraft, will start undergoing their acoustics and sign vibration testing. These are environmental tests to say that it's okay to launch in a rocket. The telescope and instruments have completed all of their environmental tests so that when the spacecraft and sunshield are complete, these two different pieces will be put together and the full observatory can go through its final testing. We expect that the launch of this will be in about 2 years from now. And when we launch it, just like Hubble's data led to the data that we learned that led to the Webb telescope, it's our expectation that we are going to learn things about the early universe that will make us want to understand it even better. And we also think we're going to learn things about other aspects of the universe, for example, exoplanets. I mentioned that Webb will also look at exoplanets. It turns out when we started Webb, there wasn't even a detection of a single exoplanet. And as we were developing Webb, we realized that it could be this really powerful device for understanding these planets around other stars. You can actually look at them as they orbit those stars, and you can measure their spectral content and understand their atmospheres. Now, Webb can do that using a technique called the transit method, and that allows Webb to understand the atmospheres of those exoplanets, perhaps looking for harbingers of life. However, Webb wasn't designed to really look for what we call sun-like planets. And we think sun-like planets are the most likely ones that we can find those aliens that we were hearing about earlier. So Webb isn't real likely to find life, but it's possible that it will find all sorts of chemical signatures that will lead us to want to understand it even better. And so I leave you with the thought that I think it's very likely that someone here today, just like when I was visiting that career fair, a few years from now will be the one to help ask the questions and answer the questions that we raise with the Webb telescope. Thank you very much.